So my talk today is focused on how to generate what we call private tabular survey data products through microdata synthetic process. So you will see that we will define the goal is to provide tabular survey data products which involve the survey weights. And in particular, we have a definition of DP that our methods can satisfy. And eventually, we're doing it through microdata synthetic process. This is joint work with Terence Savitsky from the US Bureau of Labor Statistics and Matthew R. Williams from the RTI International. Okay. So our goals, like I said, is to generate and release private tabular survey data products. You can think about them as like count tables or average salary tables as example. Moreover, we're trying to, for each table, generate the point estimates as well as the standard error estimates. Both of them satisfy a certain definition of differential privacy. Our approach is to, like I said, doing microdata synthesizers. We will do a review of what we mean by synthetic data focused on the microdata level. You will see that our model is going to be focused on how to model the outcome variables plus the survey weights plus the design variables together. The two approaches that we're going to propose, one is to model the observed sample, and the other one is directly model the population. So this is getting to the questions and challenges of how to model with survey weights. That one can be done directly on the survey sample, whereas the other one can be done on the population. And you will see that we model the survey weights together with the outcome as well as the design variables. And in particular, we're doing what we call partial synthesis. That's when you're doing synthetic data for the micro level data, that some of the variables are synthesized, whereas some of the other ones are not. We will present application to a survey of doctoral recipient sample that focus on, you will see some of the design variables like gender and field of study, as well as the outcome variable, which is the salary. And then we also design a simulation study that incorporates the informative sampling design to show that how our methods can outperform the Laplace mechanism implemented in a very straightforward way. So I'll provide some background. Probably we'll fly through the differential privacy part, but we'll talk a little bit more about synthetic data and a particular mechanism that we proposed in the past that this work is based on. I will also talk a little bit more about the survey data and the challenges come with it when you're trying to implement anything related to survey data and differential privacy. The two model, or I should say the two microdata synthesizers, we'll introduce them one by one, and we'll also introduce how we implement the Laplace mechanism with the survey weights. Then we go to the application and a simulation study, and then I will end with a few concluding remarks. So differential privacy here, I just give the basic definition over here. And you can see that later on when we're implementing the Laplace mechanism for differential privacy. So I review a little bit over here as well with the global sensitivity and everything. I just want to highlight here that when we're working with survey tables, when you have survey weights, in particular with differential privacy, when you try to implement Laplace mechanism, there are a few challenges here. I will just highlight over here. For example, you will see that we're going to have counts table, like the number of people participated in the survey, stuff like that, in the particular groups. So when we're trying to implement Laplace mechanism, some of the challenges include when you have that kind of count tables, you have some kind of sum of the constraints. So for example, we have the total number of count from female group, the total number of count from male group, and then you also will release the total amount of or the total number of participants in the combined group. So how are you supposed to reserve this kind of constraints is one of the challenges. And then of course is the survey weights, which when we get to the Laplace mechanism that we implemented, I will show you how this kind of survey weights can really affect how the global sensitivity or maybe the local sensitivity can be calculated, and the survey weights in the tables will make everything a little bit more challenging and all that. So for synthetic data, this is the one that Sasha earlier introduced as well. That's how I started getting to the statistical data privacy field that is non-formal and mostly based on Bayesian data models. So this is focused on respondent level data generation and release. Typically, you're going to estimate a model, a Bayesian model on the confidential microdata, and then you're able to simulate synthetic data from the posterior predictive distribution of the Bayesian model that you estimated. I just want to say that constructing tables based on the microdata is actually just one way to measure the data utility, because you could do many other things like regression analysis or point estimates or confidence interval estimates. What is special here is once you have your synthetic microdata, you are able to do what we call unlimited queries or unlimited inquiries over here, that you can do survey tables, you can do regression analysis, meaning that once your synthetic data, later I will introduce the model or the mechanism that we have done, that once your synthetic microdata satisfies a particular definition of differential privacy, then everything else that you do with the synthetic data is post-processing. So you're not spending any extra privacy budget when you're doing any other type of stuff, including the survey tables that we're doing here. In the past, because this is non-formal, so people will evaluate the utility, and then of course also the disclosure risk evaluation is non-formal, but nevertheless, if the models are very well designed for the data at hand, it usually will provide high utility and low risk, even though it's non-formal. So the particular mechanism that we worked in the past is actually thinking about the mechanism which we have in the DP definition in a couple of slides ago, is thinking about what we call the pseudo-posterior. So if you're familiar with the Bayesian framework, you can look at this equation 1 over here. So Y is the data, okay? And then of theta is the model parameters. So you can see here we have the likelihood of Y given theta, and then also the prior distribution of the theta. What's special here, so if you ignore the alpha I over here, it's just a regular posterior. But then if you have this alpha I, which is what we call the privacy weights, that is calculated based on after estimating the model, we have what we call the pseudo posterior, meaning that we have a privacy weight, and then you have your likelihood of any record being raised to the power of this privacy weight. And the weight that we design going to be between 0 and 1. So you can think of if your record is very highly risky, then we're going to downweigh the likelihood contribution of this record into the joint likelihood. But if your record is not very highly risky, whereas your alpha I will be close to 1, then your likelihood or your contribution to the likelihood will be much fuller, in a sense that we don't think it's very risky. So we're going to let it to be estimated together with all of the other records. So I will skip some of the detail over here, but nevertheless, I just want to say that the methods that we worked on eventually, each posterior draw after you do this posterior pseudo posterior estimation, going to provide 2 times delta alpha over here once you produce a synthetic data set Y star. So we have Y as the confidential, and then Y star is the synthetic data. So pretty much this delta alpha is related to the Lipschitz bounds, and then we have a particular way to estimate it. You will see that the epsilon here, we have a little bit on the underscript Y over here. So this is, you can consider as a local because it's very specific to the data set. But the particular method and the paper that we included over here proved a particular definition of asymptotic differential privacy, that you will be able to do this repeatedly if you want, as long as your sample size is large enough that will reach the actual global differential privacy. So I highlight over here again, if we have the synthetic data Y star, which is the micro level, and then now I wanted to produce survey tables, it's post-processing, so it's going to achieve the same differential privacy guarantee at the same time, not expending anything more from the privacy budget. Lastly, the survey data. So in case some of you are not very familiar with this kind of work and the challenges over here, we have a sample of small n individuals from a population U of a size of capital N. What's special here is each individual in the population going to have a selection probability. We use pi I to represent the selection probability that is going to contain some information about this A over here, that they will be having this probability of selected in the sample. And the informative sampling with survey weights, which you can see that the weights is inversely proportional to the selection probability. This is very typical that you're going to create estimators on the sample that you can reduce bias. And if you're working now with differential privacy and trying to provide differentially private survey data with survey weights, there's few challenges I just highlight over here that we're trying to figure out and also trying to propose our method to mitigate. First of all, is the survey weights, like I said, with the informative sampling design over here, is actually in the first place trying to mitigate the estimation bias. But at the same time, as you can see that because of survey weights, it can go like hugely large. And then once you have that, you can see that some of the individual observations going to be increased in terms of the influence. And then because of that, it will be very hard to actually add noise when you're trying to do Laplace mechanism. Second is we're trying to not only produce the point estimates when you're looking at the survey tables output, but also the variance estimates. And that's another challenge, I think, added challenge when you're trying to do differentially private point estimates, as well as the standard error or variance estimates. So at the end of the day, we're trying to have an efficient estimation of the variance, but at the same time, not spending too much epsilon as we go along. So that's the main challenge over here when you're dealing with survey data with differential privacy. So our approach, like I said, we're doing synthetic data generation and trying to model the data and then get the micro level data synthetic and then create the tabular data outputs that we want. The two synthesizers that we will produce present today, both of them based on the pseudo-posterior mechanism that I introduced earlier. We're going to look at the outcome variable as a salary, and the design variables include gender and field of study. And then we also have the survey weight. So these are the collection of the variables that we model using Bayesian methods. And then eventually we're going to generate synthetic microdata with the epsilon y equals to 2 times the delta alpha privacy guarantee. And eventually we'll be able to get field counts as well as the average salary tables. So we're going to have 2 tables in total, as you will see, with the same privacy guarantee. So the first synthesizer is what we call fully based for a sample. So we call it FBS. This is fully based, and we're jointly modeled the YN and the survey weights. On the observed sample, it's pretty straightforward. We actually just using a bivariate normal model for the YI and the WI, and the XI, which are the design variables, are part of the multivariate normal regression process. What we're going to do is, well, you model this, and then you're going to have your synthetic YI, right? And you're going to have your synthetic WI in the process. And then after that, you'll be able to come up with private tables based on the micro level data that eventually you can use combining rules to create multiple table, the final table if you want. So pretty much we still follow the very conventional, I would say, synthetic data literature that in order to capture the variability across the different copies of the synthetic data sets, we're going to simulate a little m number of posterior samples. And then what you get, you're going to have m partially synthetic data because we only generate y and w and then keep x, the design variables, as fixed. And then you're going to get your privacy guarantee as that 2 times delta alpha. And then you can create a final table, say, for the counts, and then another final table for the average salary by using combining rules that's once again coming from the synthetic data literature. So that's for the sample version. And we can also do a model on the population directly. So earlier, like the sample version is that you have to do the bias correction in the analysis stage. So you have your YI and WI. But if you're directly trying to model the population model, here we're still doing joint modeling of YN and the survey weights WN as well. The population model is following from a previous work that if your YI follows a normal model and your pi, remember pi is the selection probability, which is inversely proportional to the survey weights, then if it follows a log normal distribution, we're able to directly specify a population model. So in this case, the population bias correction already happens or takes place in the population model. So meaning that when we have our synthetic YI and synthetic pi, and from the pi, you'll be able to get your synthetic WI. You don't need to do any kind of bias correction in the analysis stage. You can directly get your population corrected point estimates and standard error estimates over there. So similarly, we do the pseudo-posterior mechanism. We have multiple synthetic data sets being generated, and then we're able to use combining rules to create using partially synthetic combining rules to create the survey tables directly. So once again, here is partial because we fix the design variables and then we only synthesize the outcome Y as well as the weights, which is from the pi I itself. So if I put them side by side, you can see that for both methods, we model the weights. I think that's a big important contribution of our work, because you will see that because of the fact that we're co-modeling the outcome variable Y as well as the weights, we're able to reduce a lot of the variation and of course result in more accurate point estimates and smaller standard error estimates as well. We also summarize here the bias correction stage for the sample. It's done at the analysis, the FBS. But then for the correction for the FBP, it's mostly happening in the synthesis process. Both of them partial synthesis, both of them synthesize the outcome and the weights and keep the design variables unsynthesized. And then the post-analysis is how we eventually being able to create the tables directly from the synthetic microdata that we get from here. One thing I want to highlight is that the model on the sample is a little bit more, actually a lot more flexible than the model on the population. So overall, even before we move in or walking into the results, I want to say that it's much easier to design a model that is for the sample than for the population. So that's the important note to keep in mind. So the Laplace mechanism, so once again, we're trying to get the counts table as well as the average salary table. So if you don't have the survey weights, then everything is pretty straightforward. It's very well studied. But because of the survey weights, you can see that the local sensitivity that we're working on here for the count now involves the weight. So you have to think about the maximum weight minus the minimum weight, which will be actually the local sensitivity for a particular cell of gender G and field F. And then the local sensitivity of the average salary will be a little bit more complicated as well. So now you can see that in equation 6, we involve the weights as well as the outcome and then trying to think about the maximum possible change. And we also had some replication method that we implemented in order to add noise to variance estimates, just to reduce the amount of noise that we have to add. So with that, I will walk into the application to survey of doctor recipients and then the simulation study that we designed, and then go to the concluding remarks. So the SDR, the survey of doctor recipients, we looked at an application, a particular sample of about 10,000 observations-ish. And you can see that we looked at the root mean square. So remember when, let me actually go here. So this is the table, like an example of the table that we actually going to get. So you can see the sample column that's from the sample itself, the Laplace column, the FBS, the first model, and the FBP, the second model. So you can see that for the sample, we have the point estimate, and then as well as the standard error estimate directly from the sample in the parentheses. And then for each of the methods, that's what we're doing. So the utility that we're checking, just to make everything a little bit easier to read, is look at the root mean square error. So that's looking at the point estimate of each method compared to the sample point estimate, and then also the variance estimate from the from each method compared to that of the sample. So with that, I want to show you the overall results, so it's much easier to read. So over here for both 3 methods, we keep the epsilon yn-ish around 10-ish, as you can see. And then we generate 3 synthetic data sets for our FBS and FBP. For the Laplace, we're just using the total budget and then adding the noise accordingly. So on the left, we have the count table, root mean square error. On the right-hand side, we have the salary table of the root mean square error. So the root mean square, basically, the lower the better, meaning that the lower the RMSE, the higher the utility. So you can see that on the count table, which we don't take into account of the Y's, the outcome, only the weights themselves, you can see that FBS, the one on the sample, is doing better than the FBP, and the Laplace is not too bad at this point, okay, as you can see. So we do this violin plots because we have so many cells that we're doing. So in total, I think we have 27 cells in total over here. But when we go to the right-hand side, which is the average salary table, you can see that the Laplace is doing much worse. Look at the scale. Okay, so the lower the better. And also, if we compare the FBS and FBP a little bit more, you can see that the FBP, when we're able to do the correction directly on the population, actually can have a better utility for the salary table compared to the FBS. Okay, so overall, you can see that the FBS and FBP both, especially for the salary table, doing much better than the Laplace mechanism. But then between the count tables as well as the salary tables, FBS is doing better on the count, whereas the FBP is doing better on the salary. And then we designed a simulation study. So one thing we found out about this particular application that we did, actually the design is not very informative, meaning that the outcome variable and the weights variable are not very highly correlated. So we actually, in our simulation study, we designed something a little bit more informative. That actually you will see that because of the co-modeling of our synthetic data models, when you have more informative sampling design, the results will be even better compared to the application that we did. So once again, we're looking at the MSE R root mean square error. We're looking at the ratio, so we're directly compared to. So once again, the smaller, the better. And like I said, this is a little bit more informative sampling design. So you can see that Laplace, even on the count table, is doing much worse compared to before. Whereas the story, I think, between FBS and FBP still stay relatively similar, that FBS is doing better on the count table, whereas the FBP is doing better on the salary table. So you might be curious why the FBP is doing better on the salary table. So here we're showing some kind of intuition behind. So on the left we have the sample scatter plot, that is the salary, the outcome variable plotted against the weight. And then the FBS and FBP, both of them are co-modeling the salary and the weight, if you remember. And you can see that the FBP is able to do smoothing much better, in a sense that it's not surprising for the salary table, which you include the salary outcome as well as the weights when you're doing the summary, is doing better compared to the FBS. So with that, I will conclude that we're, in our work, we propose formal privacy for data collected under informative sampling design between the three methods, the FBS, FBP, as well as the Laplace. We recommend the FBS as easy to estimate, as well as it produces lower root mean square error overall. The synthetic data at the micro level is privacy protected, so it will obey all constraints without any, or I should say, with post-processing, but you don't need to spend any extra budget when you're producing other products like the survey tables if you want. But with the synthetic data, you can also do, for example, like weighted regression if you want, because you still have the synthetic micro data for the weights and the outcome and the design variables. We don't really need interactive queries. The synthetic data may be used for other purposes, like what I said, regression, weighted regression. In the appendix, if you ever want to check out, I put it in the, I think it's the Google Drive box. We also propose ways that you can tune the utility risk trade-off. That's, figuring out how you can play with the epsilon a little bit, and then the higher it is, the higher the utility as well, which is a very common feature of synthetic data. The paper is published at the Journal of Survey Statistics and Methodology. I include the link over here if you're interested to check it out. When you get the chance. And here's our acknowledgement, as well as some of the references. I'm happy to take any answers if we have remaining time.